Using a substitution or a change of variables is a very common way to approach differential equations. And there are thousands of different substitutions you can use to help you solve specific type of differential equations. We're going to look at one very specific type right now. It's called a Bernoulli equation. Now, Bernoulli is a name you're going to hear a lot in the future in your classes because it was a family of them. I believe it was a father and it was either 2 or 3 sons that were pretty involved in mathematics. So when you hear the word Bernoulli, it's not necessarily all the same guy. But here's the way that they had to approach this type of differential equation. If we had an equation in the form dy dx plus some p of xy is equal to some function of x, we would say that this is a first-order linear differential equation. We know how to solve this. We would use an integrating factor. What if we add something slightly more complicated here? Instead of just having a function of x on this side, what if we have y raised to a power? Well, the way that Bernoulli, I'm not sure which one, decided to solve this is he's going to use a substitution. The substitution that you're always going to use is you're going to say let whatever letter you want, u, whatever, a lot of textbooks use z here, let z be equal to y to the 1 minus n. All right, kind of weird. Now, what is n here? Now, notice n is the power that the y was on this side. So let's take a look at a very, very straightforward example and see how this substitution is going to work. So let's say if I had, let's move it up here, and again, the directions for this are just going to be solved. If I had xy prime plus y is equal to x squared y squared. Now, before we go doing any type of substitution, you always want to put it in the correct form. And at least for our first order linear and most of our differential equations this semester, we want the highest derivative to be by itself, which means I want to take this and divide through by x. So this will be y prime plus 1 over xy is equal to xy squared. Now notice, this has this form exactly. The derivative plus some function of xy is equal to some function of x, y to a power. So the substitution we're going to say is let's let z equal y to the 1 minus n. So z is equal to y to the negative 1. All right, now since this has a derivative in it, we're going to want to replace our derivatives as well. So what we do here is take the derivative of this with respect to the independent variable. Remember, since this is y prime, our independent variable is x. So I'm going to take the derivative of this with respect to x. So I get dz dx, or z prime if you wanted to, is negative y to the negative 2, using your chain rule, dy dx, or y prime. Okay, now here's where his trick is extremely interesting. What you're going to do now is you're going to take our equation right here, the one where we already got the lead coefficient divided out, and you're going to multiply through the entire equation by this. Multiply through by the coefficient of, I'm going to say dy dx here. Now, of course, it may not be y's and x's, but same idea. So I'm going to take this equation and I'm going to multiply through by this. I'll do it in a couple steps. So I get negative y to the negative 2 y prime plus 1 over, let me write it like this. Let me go around like this. Let's see, minus y to the negative 2 times 1 over xy is equal to negative y to the negative 2 times xy squared. All right, you're going to clean this up just a little bit, and just so it kind of matches what I have going on over here, I'm going to switch to my differential notation. So dy dx minus, that's going to be 1 over x, y to the negative 1 equals negative x. All right, here is the beauty of this. Notice now, our first piece, negative y squared dy dx, is exactly what this whole piece here is, which means I'm going to replace all of that with dz dx. So that is dz dx minus Notice here, the second piece, this piece is exactly what we said z was equal to, so that's 1 over xz is equal to x. Now, with that one substitution, we've now got rid of the power on the other side. Notice there's no more y's there, so now this is a first order linear differential equation. So we would go about solving this exactly the same way. So let's see, we would use an integrating factor here. And my integrating factor is e to the integral of negative 1 over x dx, which is e to the negative natural log of the absolute value of x. I want to get rid of that absolute value here in a second, because we're going to be able to put that up. I'm going to write that real quick as x to the negative 1. I want to get rid of that absolute value. Now, I know x can't be 0 here. Let's just go ahead, and since it's inside a logarithm, let's make it positive. So let's put x on the interval, say, from 0 to infinity. That means it's positive. I can get rid of it. And notice I didn't include 0 because it's on the bottom. So if I say that that's true, then my integrating factor is just 1 over x. All right, so remember how first order linear works. We multiply through the entire equation by the integrating factor and integrate both sides. Now the good news, on the left-hand side, you always end up with the exact same thing. You end up with the integrating factor times the dependent variable. On the other side, you need to multiply and integrate. So I get 1 over xz is equal to the integral of dx. So 1 over xz is equal to just x plus an integration constant. Now, solving for z, we get z is equal to x squared plus cx. Well, that's good news and bad news, because we finished solving this differential equation. The problem is, I don't care what z equals. I didn't start with z's, which means once you solve for z, now you need to back substitute. Z is equal to y to the negative 1. So I'm going to get rid of my scratch work here for my integrating factor. And we know y to the negative 1 is equal to x squared plus cx, or 1 over y is equal to x squared plus cx, or y is equal to 1 over x squared plus cx. All right, so there is our solution. Now that we have what y equals, if we were given any initial conditions, now is when we would apply the initial conditions to figure out what our arbitrary constants were. All right, let's try another one of these. The method's going to be the same for all of them once you decide that it's the form. So let's take a look at another one that's maybe a little bit harder. What if I have xy prime minus 1 plus xy equals xy squared? All right, let's see if we can make it through this. First, anytime we're dealing with a differential equation, it's almost always a good idea to get the highest derivative alone by itself. So let's go ahead and divide through by that. So I have y prime is equal to minus 1 plus x over xy is equal to y squared. All right, this is a Bernoulli equation because it looks like a first order linear, except for we have a power of y on the right-hand side. Remember the way that we're going to do this, we're going to say let z equal to y to the 1 minus n. So this one's ends up being the same power on that side. So we get z is equal to y to the negative 1. dz dx is equal to negative y to the negative 2 dy dx. We're going to multiply through by the negative y squared. So I get negative y squared dy dx. That's with the first term. Plus that gives me 1 plus x over xy to the negative 1 is equal to negative 1. Right? Multiply this by negative 2, negative y to the negative 2. Multiply this by negative y to the negative 2. Same thing on the other side. Now our substitution should work. The first term here now is exactly what dz dx is equal to. And the y right here is what z is. So by doing our substitutions here, this equation becomes dz dx plus 1 plus x over x z is equal to negative 1. All right, this is a first order linear differential equation. So now we go back to solving that type. We know for this we're going to use an integrating factor. It's e to the integral of p of x dx. Well, to integrate that, we're actually going to want to break that up. So this is going to be 1 over x plus 1 dx. So this is e natural log absolute value of x plus x. Ooh, all right, so I can rewrite this as e to the natural log absolute value of x times e to the x. Well, just like before, I know the exponential and the log is going to cancel, and I'm just going to get the absolute value of x. I don't want that absolute value there. So again, let's go ahead and put it on some interval. Since we're not allowed to take the log of 0, let's go ahead and make sure that it's there. So this is just going to end up being x e to the x when we do that. All right, on the left-hand side, remember, what do we get? When we multiply the left-hand side by the integrating factor and integrate, you always get the integrating factor times the dependent variable. On the right-hand side, you have to multiply and integrate. All right, to integrate the right-hand side, you need to do by parts. I'm going to let the x be the piece I take the derivative of. I'm going to keep the negative out front, by the way. Just go ahead and put it out front. And dv is everything else, so that's e to the x dx. du is dx, v is just e to the x. So when we put this together, I get x e to the x times z is equal to the negative out in front of the integral. uv, that's going to be x e to the x minus, but we had a negative out front, v du, integral of e to the x dx. So x e to the x z is equal to negative x e to the x plus e to the x plus some constant. All right, let's go ahead and solve for z. Once we divide through by what's in front of z, we get z is equal to, well, x e to the x divided by x e to the x, that's just going to give me negative 1 plus 1 over x plus c over x e to the x. All right, we're almost there. Again, let's get our scratch work out of the way here. Kind of crowding up everything. So we didn't start with z's. We go back to what y is equal to. Y to the negative 1 is equal to negative 1 plus 1 over x plus c over x e to the x. Or 1 over y is equal to negative 1 plus 1 over x plus c over x e to the x. Now I can do the same thing that I did a second ago and just flip both sides, but we'd have this complex fraction. So the best thing to do here is go ahead and get a common denominator and put that together as one fraction. So hopefully you can see the least common denominator is x e to the x. It would be negative x e to the x plus e to the x plus c. Okay, so now if we flip over both sides, we get y is equal to x e to the x over, I'm going to write like this, e to the x minus x e to the x plus c. All right, so there we go. There's the solution to that differential equation. Now, if we had any initial conditions, like y of 2 equals 8, now is when we'd apply them to figure out what our arbitrary constant is. So, Bernoulli equations, a lot of this class is making sure you can recognize a form. So once you isolate the derivative, if you end up with some function of xy equals some function of xy to a power, it's a Bernoulli equation. This substitution will always turn it into a first order linear differential equation. Now, a big mistake I see on a lot of these is you forget to back substitute. So once you solve for whatever your substitution variable is, make sure that you're back substituting and then solving for that dependent variable.